Basically, I am performing the computer simulation. That is the main field of my study for the hydrogen embrittlement. But during this computer simulation, I still have some questions about the dislocation motion. So this time, I'd like to show you the very simple experiment results that shows some insights or the evidence to the computer simulation results. My interest is one of important computer simulation results is the mobility of dislocation. Especially for this one is edge dislocation mobility. Initially, we perform molecular statics analysis. That results indicates that dislocation mobility for the edge dislocation mobility increase. That we call the softening. The softening is occur at the extremely lower hydrogen concentrations. But in the ordinary case or the realistic case, only the hardening occur for the edge dislocation. That is a molecular statics results. But in counter, the Professor Matsumoto's molecular dynamics simulation that in the previous presentation, a little bit to introduce very long time, computational time is required, 2 years or 3 years, very long time. The results indicate that only the hardening, regardless of the hydrogen concentration. This is some contradictory results, but the analysis of extremely slow dislocation velocities is very difficult. And also at low velocity, the dislocation motion, move stress is very low. Those results make it difficult to identify the degree of mobility, we believe so. And a similar kind of results is reported by Itakura by the first principle calculations. That is for the skill dislocation, BCC ion. Softening is occur at the low hydrogen concentration and hardening occur at higher hydrogen concentration. But there are no experimental results or very few experimental results of softening is reported. So I'd like to try to perform the nanoindentation softening or hardening behavior. By the literature, some softening and hardening results are reported. First one is using pipeline steel X70 by Dr. Lee, Professor Lee, branding at the indented tip. That causes the hardness and the hardening. That is somehow connected with higher dislocation density at the tip, near the tip. The second one is Dr. Tomatsu performed for the pure iron. Higher dislocation density and slower indentation speed softens the material. And hydrogen trapped near the dislocation suppresses work hardening and increases mobility. They reported like this. And third one is a very interesting report. Professor Zhao performed reported in 2015. The hydrogen concentration and its gradients affect the softening and hardening of steel. So this is very interesting. So we tried to perform the similar nanoindentation test. So this to experimentally evaluate the relationship between dislocation mobility and the hydrogen concentration. Nanoindentation hardness was examined to ferritic phase of iron. So these are my statements. The upper one is S245C and polycrystalline low carbon steel. The lower one is iron silicon single crystal material. And those two materials of the ferritic phases used for the experiment. The hydrogen charging method is like this. In order to perform the nanoindentation, one side is mechanically polished at first, then put into the glass and covered like this, and the other side is hydrogen charged. The charging condition is like this. And using both, this is S25 low carbon steel and single crystal steel and hydrogen charged for 30 minutes and exposed to the atmosphere. The exposed time is changed from 0 to 216 hours. in order to change the hydrogen content within the material, then performs nanoindentation. So I'd like to explain the hardness. Hardness, as you know very well, but the hardness itself is, we think it is in the engineering field, material-specific constant. That is the hardness. And the hardness is, most of the hardness is obtained by the dividing the indentation load of the indenter by the surface area, like this equation. So this is F is a force and H is the indent depth. That means A and B is a convert coefficient, and this H is the usual engineering hardness. By this equation, changing the formula, the loading force F can be written like this. As you can see here, the indentation force is expressed on the function of the indent depth H, second order of the equation. Since the hardness is a constant, so the indentation load is a quadratic function of the indent depth like this. And next step, integrating the indentation load F with integral depth H is in the indentation work W. That is the function of also the H like this. Since the indentation volume B is also the cubic function of H, the macroscopic hardness can be interpreted as the indentation work per indenter volume multiplied by a constant like this. In counter for the elastic deformation during the initial stage of indentation, elastic constant theory was used to calculate. That is expressed like this equation. The R is the spherical radius of the spherical indenter, and H is the indentation depth. E star is the elastic modulus calculated by this equation. Since E star and R is a constant, that means from this equation that indentation load is a 1.5 degree function of the indentation depth as the initial elastic indentation like this. The degree of the polynomial should change from 1.5 at the initial state, elastic state, to the 2. That is the material constant as the hardness. But in the nanoindentation test, the load displacement relationship agrees well with the health this 1.5 degree. This theory, even including plastic deformation. But we have to pay attention that the physical meaning of this is not different for the elastic case, and this nanoindentation test results. Anyway, the change in the indentation load caused by the hydrogen charge delta F is written like this equation. The alphas change without hydrogen and with hydrogen cases. By integrating this delta F with H, the change in indentation work delta W caused by hydrogen charging can be obtained like this. Here, in my experiment, we used that triangle pyramidal indenter shape. So 115 degrees angle. So using this, considering this shape, identical shape of the indenter, the volume of the indentation volume is written like this, and beta is calculated by the geometrically, let's say also near the 8. And using this, the volume divided here, and delta W is here. Therefore, the change in work by indentation volume, that is the micro hardness. Here we talk about hardness caused by the hydrogen charges, then like this equation. Okay, this is the experimental results. The left-hand side is the low carbon polycrystalline steel. The right-hand side is a single crystalline iron silicon material. The gray dotted point is the low data, and the broken line and red line is approximated by the 1.5 degree of this equation. As you can see, all the results, the 1.5 degree function, Hertz constant, Hertz equation can well fit it. And next, using the function delta F this equation. All the experimental data is plotted like this, polycrystalline and single crystals. The indentation load due to hydrogen charge was the largest at 0 hour, that is immediately after the hydrogen charging. As the exposure time to air increased, the change in indentation load due to hydrogen gradually become negative, like this. And in both materials reaches their minimum value after 72 hour and 72 hour and 48 hour of exposure time, respectively. After a long exposure time, over the 96 or like that, the effect of hydrogen change become almost zero, like this, 144 and 168, like this. And this is the results of the previous slide. Horizontal axis is the exposure time, and the vertical axis is the difference in hydrogen-induced work per unit volume, calculated by this equation. The hardest hardening occurs at 0 hour. Indent depth is changed from 10 to 50 nanometer because this is the equation and the function of the indentation depth h. So we change the indentation depth 10 to 50. The hardest hardening occurs 0 hour after hydrogen charging, the first one. And second one, the hardness decreases with exposure time like this, and return to the same level as that of the uncharged specimen. The original state, beautifully recovered. As the indentation depth increases, the effect of hydrogen decreases, but this is due to the fact that the evaluation equation converges to 0 at h increase like this equation. This trend is inevitable when the degree of the polynomial approximation of the indentation load f to h is less than 2, and it's due to maybe the plastic deformation, I think. And this is also the error bar of the S245 polycrystalline results. And in both cases, those are the 50 nanometer of indentation depths. And next, we perform the thermal desorption analysis. This is a S245C case at the immediately after the hydrogen charging. Exactly, hydrogen exists and 1 day's exposed exists, but 2 days there's no hydrogen can be detected. But the hydrogen concentration is estimated to be below the detection sensitivity of the gas chromatograph using in this experiment. And also the single crystal does not detect the hydrogen content by my equipment. So we believe this change is attributed to the hydrogen concentration. And we don't have enough time, so this is a quantitative variation. But this softening and hardening is efficiently affected, I believe. Those are my conclusions. Thank you for kind attention. And my results is published in this paper. Thank you.